Hi students, so let us start with the new concept today, that is paging. So paging is a concept of memory management. So before starting with paging concept, let us see certain basics of paging. Earlier we had studied about the topic contiguous memory allocation techniques. Now what the name itself suggests, what do you mean by contiguous? Contiguous is nothing but continuous. Now if you see this particular diagram, this is a particular memory represented, and let's say this is a there are multiple processes residing in this memory. Let's say there are two processes P1 and process P2. Now when process P1 is allocated space in memory in a continuous fashion, then it is called as continuous memory allocation. So we had studied about the two techniques such as static memory allocation and dynamic memory allocation. When we had studied static memory allocation, it faced with a challenge such as internal fragmentation. Then we studied about dynamic memory allocation, who faced with a disadvantage such as external fragmentation. Then we saw its solutions such as compaction, wherein all the free spaces available in the memory were compacted or combined together, and then that space was used by the process for its execution. However, it again faced with certain disadvantage, wherein the CPU utilization was less, memory utilization was more, but CPU utilization was less. So to overcome this advantage of CPU utilization, we came up with a solution, that is to move from contiguous memory allocation to non-contiguous memory allocation. Now what do you mean by non-contiguous memory allocation? It is just the opposite of contiguous memory allocation. In non-contiguous memory allocation, what happens? Let us see this diagram particularly. Let's say again there are three processes, process P1, P2 and P3. Now the first space has been occupied by process P3. Then again here some process is occupying it, this particular space, and P2 is occupied this space. Now these two spaces are available. Now P1 comes, and P1 does not have continuous spaces in continuous space available in the memory for its execution. So whatever space is available in the memory for its execution, that will be used by P1 and will continue its execution. So this is non-contiguous memory allocation. So let us see the definition. It assigns the separate memory blocks at the different locations in main memory in non-continuous manner to the requesting process. So this is a non-continuous manner. It is not in a continuous fashion. So how can this be achieved? This can be achieved with one of the memory management technique, that is called as paging. Now let us see into it. Now, as I've already told you many times, that whenever a program wants to execute, it becomes a process, and any process that is executing will be always in main memory. So let us say this is a program, or let's say this is a program which is residing into secondary storage device, or we can call it as a logical memory, and this is divided into equal size of blocks. All, if you can see, all the blocks are of 2 KB. Okay, all when the logical memory or the program is divided into equal size of blocks, which is stored on a secondary storage device, those equal size of blocks are called as pages. So these are called pages. Okay. Now, when the main memory, or we can say it as a physical memory, or we can say it as a RAM. Now when we have to bring the program from the secondary storage device to the main memory for its execution. Now when the main memory is divided into equal size of blocks, they are called as frames. Now this page page and this frame should be of equal size, so that when I want to bring this particular page into the main memory, it should occupy itself. So the page number, so the page size and the frame size should be same. So what is the paging? To put the pages into the frames in main memory is called paging concept. Here now let us take one example. Let's say there is a CPU. CPU wants to access a data which is stored on this location. Before that, let us see, this is a process P1 which is divided, which is stored on a secondary storage device and which is of size 4 byte. So the process size is of 4 byte. Now the page size that has been given to us is 2 bytes. That means each page will be of 2 bytes. So how many pages in all? If the process size is 4 bytes and if one page is of 2 bytes, obviously there will be 2 pages. So here if you can see, page number 0, page number 1. So the process is on, this process is stored on a secondary storage device whose size is 4 bytes and which has 2 pages in it, each page having the size of 2 bytes. So these are the bytes, 1 byte, 2 byte, 1 byte, 2 byte. Each page will have 2 bytes. This is page number 1, this is page number 2. I mean to say page number 0, page number 1. So in all how many pages? 2 pages. So how it can be calculated? Number of pages divided by process. So number of pages are number of pages can be calculated as process size divided by number of pages. What is the process size? 4 bytes divided by 2 bytes. That means how many pages? 2 pages. So 2 pages. Now in the similar manner in the main memory. In the main memory, what is the size of the main memory? This we have assumed. The assumption of the main memory is, let's say, 16 bytes. If it is 16 bytes and earlier I told you the page size and the frame size should be similar, so that the page in the main page in the secondary storage can be easily brought into the frames of the main memory. So the page size and the frame size should always be same. So this is 2 bytes. That means obviously this will be also of 2 bytes. So frame size of 2 bytes. Then how to find out the number of frames? Number of frames is equal to main memory size divided by the frame size. So how many frames in all? 8 frames. So if you can see, if we start from frame size, frame number 0, it will end up to 7. So in all 8, 1, 2, 3, 4, 5, 6, 7, 8. 8 frames. Again the size is of 2 bytes. So 1 byte, 2 byte, 1 byte, 2 byte. So each frame will have 2 bytes into it. Okay, now as I've told you, page size and the frame size should always be same. So why? That is also mentioned that the entire page in the secondary storage should fit into the frames in the main memory. So now let us consider an example wherein the CPU wants to access the data which is stored at byte 3, which is a position on page number 1 of process number 1. Okay, now CPU knows only that the data is of process P1 and this is on the secondary storage device. However, this particular data at byte number 3 is located somewhere in the main memory and in the frames of the main memory. That particular mapping is not known to CPU. So how do we do that? That is called as mapping. That mapping is done by one memory management unit. That memory management unit in paging is called as page tables. So let us see. So this is the paging architecture. Now let us see. CPU wants to access the data at position number byte number 3. Now that is the logical. LA stands for logical address. That is the logical address wherein that particular data is stored on the secondary storage device. But it does not know its physical address. Physical address is the address wherein that particular data is stored on the main memory. CPU does not know this particular address. CPU only knows that the data is present over here. The mapping between the logical address and the physical address is done by some memory management unit. This memory management unit is called as a page table in paging. So this is the mapping table which is used in paging. Now this page table will have, or its contents are the frame numbers in the physical memory. The frame numbers which are there, or the main memory is divided into number of frames. Those frame numbers are present into this page table. So how do we do that? Before that, to calculate the logical address, there are two things needed. One is P and the other one is D. P stands for page number. As CPU deals with the logical address, P stands for page number, D stands for page offset or page size. Then in physical address will deal with the physical memory, which means physical memory is main memory and main memory is divided into frames. So it will deal with F stands for frame number and D stands for frame size or frame displacement. So based on this, now we will see how CPU will get the access to a particular data position on byte number 3. Now see, this is the CPU. CPU wants to access, as per the earlier diagram, paging architecture diagram, CPU wants to access the data which is present at byte number 3. Okay. Now, CPU knows that CPU wants to access this, but the CPU does not know that this particular data is present somewhere there in the main memory. That position is not known to the CPU. So the mapping of from here to here is done by the page table. Is done by what? The page table. The page table of this particular process. This is process P1. Each process will have its own page table, and as I've already told you, the contents of page table are what? Frame numbers. Frame numbers from the main memory. Now how do we do that? Just I'll tell you that. So as I've told you, CPU will work on logical address, and here it will convert the logical address into the physical address of the to calculate the physical address of the main memory. Now to calculate the logical address, how does it do that? So as I've told you, it uses two things. One is page number and D stands for page size or page displacement. Now what are the number of pages? How many number of pages here for process P1? 2 pages. So 2. Now how this 2 can be represented in binary? It can be represented by 2 digits, 0 and 1. Okay. So the 2 can be represented as 0 and 1. So how many bits to represent 0? 1 bit. How many bits to represent 1? 1 bit. So can we say that page number will require only 1 bit to represent? Yes. Page number will be of, this field will be of 1 bit. Then the next field is what? D. D stands for page size or page displacement. Now what is the page size? Page size is of 2 bytes. 2 bytes how? 1 byte, 2 bytes. 1 byte, 2 byte. So page size is of 2 bytes. Again 2 can be represented as 0 and 1. So page size field is also of 1 bit. So page size is also of 1 bit. Now how to represent 3? How to represent this 3? So see, where is this 3 located? On which page number? We are calculating the page number. Is it located on page number 0 or page number 1? It is located on page number 1. So 1 will be the content of this particular field. Now what is page displacement or page size? Now page displacement or page size is on which position on which position that particular data is present. Now this is the 0th position, this is the first position, this is the 0th position, this is the first position. So on page number 1, 3 is placed on the first position. So here I will write 1. So what are the contents? 1 and 1. So if you represent 1 and 1 into binary, it stands or it represents 3. So so the decimal equivalent of binary 1 1 is 3. So this is how we got 3. Now this we will move to the page table. Now what happens in page table? Page table has the frame numbers. Now this page number 0 is represented over here and page number 1 is represented over here. Now the contents of this page number 0 and page number 1 are present in frame numbers 2 and frame number 4. Now let us see how do we do that. So see, if you see over here, page number 0 and page number 1 are already occupied. They are occupied. Now there is frame number 2 which contains the page 0 of process P1. So automatically page number 0 will be mapped to frame number 2. The data 0 and 1 of page number 0 will be mapped to data 4 and 5 of frame number 2. Similarly, if we move to the next frame, F3, which is again occupied or filled by some another process, then comes the next process P4, F4, next frame, that is frame 4, which is occupied by the page number 1 of process P1. So page number 1 is this. The contents of page number 1 are 2 and 3. This 2 and 3 will be mapped to the data, to the byte 8 and 9 of frame number 4. So see here, frame number 4 will go here, frame number 2 will go here. Is it okay? Then after this, how to calculate the physical address? So physical address, for calculating the physical address, we require two things. One was F, one was D. F stands for frame number, D stands for frame size or frame displacement. Now how do we do that? Again we have to check the number of frames. How many number of frames? 0 to 7. 0 to 7, that means 8. So in binary the 8 can be represented from 0 to 7. To represent the highest number 7, how many bits are required? 3 bits are required. So 0 will be represented by 0 0 0, 7 will be represented by 1 1 1. So 8 can be represented using 3 bits, that means 0 0 0 3 bits, 1 1 1 3 bits. So this particular frame number field will be of 3 bits. And again we have seen earlier, page size should be equal to the frame size. So page size is 2 bytes, so frame size will obviously be 2 bytes. So 2 can be represented as 0, 1. So frame size field is 1 bit. So page size field is 1 bit. So both are same. Page size field is also 1 bit, frame size bit also 1 bit. So here frame size field is also of 1 bit. So total physical address will be of 4 bits. Now we know that this particular 3, when I say page number, I want to access this data at 3. So I will calculate the logical address. I will find out that it is on page number 1. This page number 1 is mapping to frame number 4 in main memory, and then frame number 4. How do we do that? Frame number 4. Frame number 4 is represented by 3 bits. So how is 4 represented in binary? 1 0 0. Then frame size, that is frame displacement. In frame number 4, it is positioned on the second byte. 8 and 9, it is positioned on the second byte. See, it is positioned on the second, or let's say 0th position, first position. So on the page, frame number 4, 0th position and first position. So it is positioned on the first byte. That is why it is 1 over here. So now 1001. is the binary equivalent of 9. So now we know that the data that is required by the CPU at position number 3 or at byte number 3 is located at frame number 4, byte number 9 in main memory. So this is how the paging scheme works. And with this, CPU utilization increases, which was the disadvantage or demerit of the compaction or contiguous memory allocation, which has been overcome in this non-contiguous memory allocation technique. Thank you.